Alright, so one of the biggest purchases we need for this project is an air pump, because we need to pump air through the ozone generator to keep it cool and also, you know, to actually get the ozone flowing and everything like that. So I bought this fairly crappy air pump. It is meant for inflating mattresses apparently, and it works reasonably well. Got it plugged in. Doesn't sound too good. There's definitely, you know, good airflow out of there, and it's got these couple of adapters. So that's all good. Its airspeed setting though, especially if we have to use an adapter, say like this one, the airspeed is quite high and it limits its usefulness if it is only one speed. So this is where this circuit comes in. So this is a Pwm controller, so it's a pulse width modulation, and that changes the speed of DC motors. Apparently, kind of learning some electronics on the fly here. Cut the line here, put this circuit in, and then here hopefully we'll be able to turn this knob and change the air speed. Plugged in and the capacitors haven't blown up, so let's try it. Oh, that's beautiful. Oh, you bloody beauty. So another purchase for this project. Everything's a bit of a mess, but this black tubing here is a special kind of tubing. It's called Viton Tubing. It's quite expensive. This 1 meter costs me, I think, $40, which, you know, I don't think is a good price for it anyway. It is quite expensive, especially when you're only buying, you know, short lengths of it. You're not trying to buy a kilometer of tubing. You're only buying, you know, a meter. Why I've got it and why it's so expensive is it's actually mostly made of Teflon. So it's a fluoropolymer. So once again, it is very inert. Last video, I was using my 100% Teflon tubing. This is, of course, like, you know, practically completely inert. The big problem with this is the physical properties of this tubing are absolutely dreadful. Like, this curve has to say this curve, you know, it's hard to put things in the end of it because it's completely non-stick. It's just really bad. So this tubing has basically the same chemical resistance, except actually is flexible, put bends in it, and it's all fine. So this should stay resistant to the ozone. It's not very good against like solvents like acetone and aromatics, so it's not like the perfect all-round tubing, but I think here against the ozone it'll be really good. Right, I might just turn it on, just the fan part, not the ozone tube just yet. I'll show you that it works. That turns on, that lights up, that's our circuit there. No bubbles coming out of there, but we can turn the fan up. Excellent. So everything's a mess, but it does show you that the air is going in here, going through the tube here, coming through the Viton tubing, and going through the glass thing. So there's a lot of Teflon tape holding everything together, but I love Teflon tape, and of course that'll stay resistant to the ozone. So I got a few messages about this project from people who said that they might be interested in doing this themselves because they've got an ozone generator for whatever reason and they'd like to be able to titrate it. And that wasn't actually something I'd thought of. We're going to try and do this ozone titration without any volume measurements. We're going to use purely a scale here and just 2 chemicals, both of which are fairly cheap. This first chemical here is potassium iodide. It's not really available over the counter anywhere, but online it's fairly cheap. I reckon this 100 grams I got it on special. I think it cost me $5 or something like that with free shipping. It took like 2 months to turn up, but that's not really the point. This other chemical here was a bit more expensive, but once again, as I've always said, there's always a bit of a premium when you buy things over the counter as opposed to online, is sodium thiosulfate. 985 grams per kilogram sodium thiosulfate, and it was $18 for 500 grams, which if I bought it online probably would have only been $10, but you know, it might have taken 2 months to get here once again. I was a little bit worried when it said 985 grams because I thought, oh, that's only 98.5% pure. It might be really dirty and all the crystals could be really impure, but wait till you get a look at these crystals that bloody come in this product. Look at the size of these crystals. Look at these bad boys. That's the purest over-the-counter, the purest appearing over-the-counter product I've ever seen. Alright, so the first thing I'm going to do is I'm going to put 500 grams of water in here. There you go. 500.3, good. Now I was going to use this scale for everything in this video, but it only reads it to 1 decimal point, and I thought about it, and that's really just not good enough accuracy. I think ideally we'd want a 500 gram scale that read to 2 decimal points. This one should be, it's labelled as 500 grams, 0.01 grams, so it should read to 2 decimal points, and that's what I bought it for, and they sold me one that only read to 1 decimal point, so I should have given them a bad review on eBay. But anyway, so what we're going to be doing is we're going to be using this scale just for this little bit. And the first thing we're going to weigh out is 3.72 grams of the sodium thiosulfate. Alright, now we're going to be putting all of this crystals, I put some in already, we're going to put all these crystals in one of these 500ml containers. Now we'll put the lid on, see those crystals down the bottom, we'll dissolve them all up. Now for a very important step, labelling, because we're going to be dealing with 2 clear solutions here and we can't get them confused. This is thiosulfate. This is a small side note, but do you know I have a circularly polarized filter on my front of my lens, and it helps with a lot of the glass reflection. One of the cool things I can do with it is I can decide if you want to see the screen or not. So if I turn it, hold on. Yeah, and then bye. So I can film this whole thing like this, and then you can't see the numbers, or you film like this and you can see the numbers even better than I can, really. So okay, we want 4.98 grams of potassium iodide. And just like before, we're going to dissolve this 4.98 grams in the 500 mils we have here in the unlabeled bottle, not the one with the thiosulfate in it. We'll keep them apart from each other. Dissolve it all up. It should dissolve really easily. Now we're going to weigh out an exact amount of iodide solution. We'll go, let's say 20 grams. Yeah, my chemistry degree was worth something. Now we're going to record all the values up here on the board. I'll explain what all the columns are as we get to them. My writing is a bit hard to read sometimes, but we have this first value here, and now we have to titrate it, put some ozone through the solution. Alright, so we're just going to try the pump first, which is, make sure I get this right, this one here. So flick that on, and that light turns on, and then this one here. Oh, you can't even see the thing. It's out of shot. Alright. See, it's just bubbling there. Something like that. We'll try that. Alright, so I've got my timer here. I'll chuck the fan on. I'm calling it a fan. Is a fan the right terminology? Maybe pump. We'll call it pump. I'll turn the pump on first, and then I'm going to start the timer when I flick the ozone generator on. So 3, 2, 1. And nothing. Alright, we got absolutely no colour change, even when I added the starch indicator. Over 3 minutes of ozone production. Possibility that we're now generating no ozone, but we did generate some ozone before. So let's try and blame something else first. And my first blame maybe falls on the totally legit $5 completely unmarked iodide. Why don't we get my other iodide out, and sodium iodide, put some in and see if the ozone generator works then. Right, it looks like I was correct to put my blame on the totally legit $5 iodide. I wonder what it is then. What chemical did they ship me? That's hilarious. Alright, so in conclusion, this is definitely not potassium iodide. And now that I think about it, it's far too light to be potassium iodide. So I generally have no idea what it could be. It could be anything. They've just sent me the wrong chemical. So who knows? Guess we'll find out in another video. But for now, I guess I'll continue on my sodium iodide. I've remade the iodide solution using my sodium iodide, which I know is good. I'm just going to dilute it once again slightly. And we're going to be running it for 3 minutes this time. So I've updated those numbers on the board. 40.6 grams of iodide and 0.05 is 3 minutes. Alright, so now we have a certain amount of iodine that's dissolved into solution here, and we're going to be adding thiosulfate to it on the scales, and then we can work out exactly how much iodine is now in solution. Alright, that happened so much faster than I thought it would. That means we didn't really have much iodine in there at all. Got a measured mass of 4.5. I'm just going to go with 4 for this very first rough one. We're going to put in 4, where's my chalk there? Alright, I don't know why I put in that unreacted iodide column. We don't need it. We actually don't need this moles of iodine either. Using the moles of thiosulfate, we know from looking at the reaction equations that we divide that by 2, and that's the amount of ozone that was initially reacted with the iodine. So this is 0.06 depressingly. And this is in millimoles as well. These are all millimoles. And now we can use the molecular weight of ozone, which is 48, to work out how many grams and how many grams per hour, looking at that time there. And these numbers are depressingly small. It's only 3 milligrams of ozone and only about 60 milligrams of ozone per hour. That's 0.057 grams of ozone per hour. So that's a lot less than it should be. And that's why I was surprised when it only took a very small amount, only 4 grams or so of thiosulfate solution. Remember when we got sold this ozone kit, it was marketed as a 3 gram an hour setup. So 3 grams an hour is a lot more than 60 milligrams an hour. They look like there were really big bubbles coming out of solution, and a lot of that gas was reaching the surface without touching the solution. So if we have stirring going, which is what I'm going to do now, is I'm going to set up the same experiment but with stirring, we should see a big increase in that number. So when it gets to this very light yellow stage, what we can do is we can add some of our starch. This is just some of our spray starch. So this is a good indicator for iodine, sorry. You can see that color change. That should go completely clear once we add enough thiosulfate in. Oh, I have to take off that mass, but. So the time once again was 0.05. The end thiosulfate, if we take off the 0.4 of the starch that we added, we actually only get 4.2 grams. So this 4 was probably definitely an overestimate. Yes, depressingly, the numbers don't really improve. 0.06, we're still 1.5 orders of magnitude too low. I'm going to do one more thing before going to bed, and that's do the same experiment just over a longer time scale, because maybe the ozone generator doesn't work very well on the initial warm-up. So it's maybe in the first 2 minutes or so it doesn't work too well. Let's see if it runs for, let's say, 12 minutes. So I'm going to get to titrating that ozone in a second, but I think it's also worthwhile. 12 minutes of runtime is the longest I've ever run any of this, so I think it's worthwhile to have a look. See if anything is in particular heated up. This tube seems alright. It's not even noticeably warm. Well, that's a bit warm, this one here. Yeah, see, that's... Yeah, so the ambient temperature is about 15 degrees and this is about 30, so this is generating quite a bit of heat. And that's really good, actually. I was expecting things to be a lot more heated up and mangled after a long run like that, but it looks like it can handle that kind of run time. So this is possibly the worst result. Even though it's 4 times as long, we actually have less iodine produced. So rate of ozone in grams per hour is a sixth of what the previous run was. Doesn't seem to be a great deal of consistency, and also those numbers are very, very low, so well, I'll have to really think about this. I feel like a lot of the ozone is escaping. You probably question why I've only got 40 mils in here, why I don't just fill this up all the way to the top. Well, the reason is the gas comes out, the pump is working fine, but if we put this tip just a bit lower, it stops because there's just not much pressure in the line. So if we go too far, too low, and there's too much water, it balances out and we don't actually get any gas coming out of the tubing. I've taped around here because I found that a lot of the excess air, instead of coming out here, was actually coming out all this top here. So this tape helps to increase the pressure in the line a bit. These inputs here are very small, so it's going from quite a large nozzle down to something very small, comes out this side very small again. So that really narrow nozzle doesn't really help the flow rate very much. Yeah. Oops, it looks like I was a bit too enthusiastic with the stirring. Definitely smashed that glass tip. Ooh. I did some reading as well, and I think there's a risk of iodate formation. So that's the ozone reacting with the formed iodine to go on and form iodate. It's probably only a very small error, but we're going to account for that by acidifying the solution just before adding the sodium thiosulfate. And that will cause any iodate that's formed to turn back into iodine. That'll correct that error if there is any. Might as well quickly measure the pH after the ozone has been through it. And yeah, that's quite basic, so you can correct that with just some dilute sulfuric acid, so that's not a worry. And amazingly, when we acidify it, we see a colour change. Lots more iodine formed. So maybe iodate formation is a significant error. Alright. Look at that number, that is so much nicer. So we get to go to our board, 0.1 is 6 minutes, and it is 23.3. Excellent, that is so much better. 168 milligrams per hour of ozone. It's still not 3 grams, but it's a whole lot better than 10 milligrams per hour. In fact, this correction for iodate explains another one of the mysteries we had the other day, where the long run actually produced less iodine overall than the shorter runs. Over time, we do a longer run, so 12 minutes instead of 3 minutes. That iodine was reacting with the ozone to form iodate, which was getting missed in our titration. That's why we had a much lower number for the long run. But now we correct for it, we can do just a couple more, and let's see if this number stays consistent over a couple of different time periods. So just ran it for 15 minutes there, which is a new record for length of time I've run it for, and I've been running it quite a bit today, and I just checked the temperature of this, and this in some spots is getting very hot. Over 70 degrees. I think everything else appears to be fine. Assume this is alright because the airflow, but this doesn't have any airflow, so it kind of sits here and heats up. Alright, I'll do one more final run. I've got the stirring really good with this one, I think. It looks like the gas is being really well dispersed in there. So this final row, look how good this is, 66 grams. Gives us a total of 238 milligrams of ozone per hour. Another factor I didn't think would make that much of an influence, but looking it up actually does make a big influence on the ozone production rates, is the relative humidity. So this final run here, I did today, and it's not humid at all. Whereas this previous previous runs, in between that first run and the last run, a thunderstorm rolled in. So I think the relative humidity basically doubled between that first and that last run. There was about 2 hours between the first and the last run because I'm just very slow at what I do. So if we think about this 3 grams an hour as being only for pure dry oxygen gas being fed to the ozone generator, which we didn't know, we actually thought maybe this 3 grams an hour is for just under ordinary room temperature conditions. We have that 3,000 milligrams an hour, so if we times it by 0.21, we get to what we can achieve under normal atmosphere. And this 0.5 factor here is about the stirring. So if we say really only half of the gas that was produced was accessible by the solution. So in those bubbles, only half of that gas volume actually interacted with the solution. I think that's a reasonable number. And this 0.75 is a humidity factor. So for these earlier ones where the humidity was quite high, I reckon we were losing, looking at the numbers online, probably 60% of the efficiency of the ozone generator just because the amount of water that was going in the input gas. Today, when the relative humidity was quite low, I put it down as a 25% loss, so that 0.75 is a humidity factor. So if we take all these things into account, the number we're getting now of 230 is exactly, what we've taken. So I've obviously tailored these factors. While this ozone generator has been misrepresented by giving us a number that's only achievable if we feed it dry, pure oxygen gas, it's not actually incorrect. There's actually a lot to do. I want to make it a lot neater. There's got to be safer. Got to think about drying the gas. Got to think about cooling. But this is a good starting point. So I hope you enjoyed this episode, and I'm excited to see what happens in the future to get this whole setup a lot nicer.